So CNC, computerized numerical control. So CNC machines controlled by CAD software. So we have M and G codes. So either traditional subtractive processing like lathe mill cutting or 3D meter printing with the direct energy deposition laser or electron beam. So I just want to find an example for you. Is the system fabricated by DMG Mori. So for the moment, they are among the leading companies that provide the 3D printing system, and even the hybrid manufacturing system combining 3D printing and subtractive machining system like CNC. So the combination between the CNC system and and the 3D printing system in one system only. So that can be offered by DMG Mori in Germany. The CNC has the ability to how can I say, for the complex motion control and high precision. We know that for sure is better than AM. So therefore, after the additive manufacturing process, we need the post machining with the CNC. Mhm. And has the ability to execute large CNC files. And I have already mentioned about the hybrid AM system, where we can integrate the AM system into the traditional machining centers. Yes, in order to how can I say, uh, fabricate the part. On the one side, we can save material by the use of additive manufacturing, but on the other side, we can use the traditional manufacturing like cutting in order to eliminate uh, small amount of the material from the 3D printed part in order to improve surface quality of the fabricated parts. Yeah, so there are several video clips and you could see at home if you want. So I think is there instruction about the CNC and probably the combination of CNC system and additive manufacturing system in a single system. Robotics. So we know that a robot is a human-like machine, and because, for example, it has an arm. Yeah. So like so we can call robotic arms. Yeah. The AM and the use of additive manufacturing and CNC offer a high degree of articulation. Articulation nó là một dạng chuyển động khớp. Yeah. Flexibility, advanced sensing, and control for the manufacturing process. And I'm pretty sure that robotic arms can offer or can use for assembly, for welding, wet cladding, and can accommodate the need for 3D printing, especially for 3D meter printing, to create the complex 3D design, large object, at least larger than in the case that the object built with the Photoback fusion. Yes, can deposit the material with complex part and movable platform. And for sure, this can be used for mass production, enhanced manufacturing environments, because we do need the presence of the human here. The robots can be modified or customized to serve their own needs, of course. It depends on the purpose of using the robot. Yeah. So, and the last slide highlights some information regarding the monitoring and real-time control. Yeah. So one of the example I could find for you is regarding the pattern developed by Norsk Titanium, so a company in Norway that used the some kind of plasma as a heat source in order to melt the titanium wire to deposit on the substrate to fabricate the near shape component for aerospace industry. Yes, so they have tested their product and they said that the quality of the additively manufactured parts are comparable with the rugged titanium. So properties is quite great. It's faster, it's safe material, yeah. So quite suitable for contributing to shape the path toward a more sustainable futures for the safe materials. Save the energy during the manufacturing process. Yes, and um, and can create light parts. Yeah. Or improve the efficiency of fuel consumption for several type of machines or even airplane. Hopefully, the additive manufacturing, yes, I would say contain wide range or have wide range of control options and the ability to incorporate sensor feedback for control. And I was talking about the case of an additive manufacturing system developed by Norsk Titanium, and their feedback system actually uh, collect 600 data points per second. Yes, in order to uh, control the process of printing. So if there is unreasonable parameters has been detected, and then the system can modify the printing parameters in order to control the qualities of the part after the process. So 600 data points per second. Yeah. The meta processing, yes, by additive manufacturing using the heat source as an arc, laser, or electron beam, generally harsh, so it's not friendly to human. Dynamic, poor observation is occur at high temperatures and inside the building chamber. So how can we observe? Yeah, it's generally hard to do. And happening at high temperatures, light, radiation, and rapid change in the process conditions. And as a result, reduce the system performance for sure. That's why you need or people propose you a different kind of sensor. Yes, multi-channel high-speed computer-based data collections and analyze software in order to understand the processing parameters and to control the process operations. Yes, to overcome or to solve any kind of issue regarding the process disturbance, to guarantee uh, the quality of the part. Very understandable. Yeah. They also equip inside the AM system with a high resolution real-time digital camera monitoring. Yes, to provide some kind of real-time views of the process and recording data. Uh, the laser profiling system, the pyrometer-based sensing. Yes, several type of devices equipped in the AM system in order to monitor. Yes, the process of printing. And for the AM machines, we know that we need the layer by layer monitoring the thermal conditions. Yes, because why? I do not remember exactly, but within the chapter 6 or 7, you will somehow investigate about the influence of printing parameters on uh, on whether or not you have the defects inside the fabricated part or inside the additively manufactured part. Because if you scan with relatively fast scanning speed, and then the heat provided by the heat source to the powders, for example, which is not enough for melt the powders. In that case, you have the defects of lack of fusion, and you have porosity. You have the reason this is not fused, this is not melted. Yeah. So these are the defects and need to be avoided. And if this happens, and the software should or the system should detect these parameters and provide some kind of modification. Yeah. To guarantee the qualities of the 3D printing process, and so on. And needless to say, you need to control the oxygen concentration. Yeah, because everything is occur inside the building chamber at high temperature. So without gas flow, the inert gas flow, it's easy to have some kind of oxidation reactions and modify the properties of the material, and you have some kind of rust. Yeah, which is not good. Detrimental factor to the properties of the materials. Laser power. If the laser power is large enough, and then remember spattering and the vaporization of the low melting temperature alloying elements, and then the chemical composition is changed. Yes, cooling system. Yeah, you need to cool the system to provide some kind of temperature control, to reduce some kind of thermal gradient. Platform position, dosing system. How to explain this for you? Dạng như là định lượng, cái hệ thống định lượng. Một cái dose thì là một cái thìa hay cái gì đấy chẳng hạn, một cái liều hay một cái định lượng nào đó. Air circulation and so on. Yeah. So now we can start with the chapter 5. So I think I will try to complete half of the chapter 5 today. And we have 1.5 days left. So for the next Thursday, we have the 7th day, and the last day we have 2 remaining teaching hours left. And so I think it's enough. These hours are enough in order to complete everything that have been prepared on slides. Yes. By the way, do you have any question regarding the chapter 4? No? No. Okay. And please keep in mind that the lectures have already been uploaded on the LMS. Some can contain some kind of mistake, and I will try to correct the mistake as soon as possible. And regarding the assignments that you need to carry out and you need to complete at the end of the semester, several students have asked me about the group working. And so far, I would like to remind you that it's not compulsory or it's not mandatory to do it in group. But at least you need to define a paper to refer to together. So it means that 2 students within the group need to refer to the same papers. And once you define the paper, and then you can work alone, and you do not need to care about the other. It's up to you, especially despite the fact that I encourage you to work together because it's time for you to practice. But it's up to you. It's up to you. The the second thing I would like to tell you, probably the monitor of the class had already informed you, or you already read the information on the LMS. But just to remind you about, in the case that one students inside a group of a group, for any reason cannot be contacted by the other, or the guys uh, have already left the class, and in that case the remaining student has the right to propose the paper to refer to when writing down the assignment. Yeah. And for example, at the end of the semester, if the other student occur and express a wish of doing the assignment for the evaluation, in that case, the guy must follow the proposal done by the first student. Just the case, just the case. And this apply for both the aerospace material costs and the additive manufacturing costs as well. Okay, so now let me continue with the design for additive manufacturing. This is in one of the most important chapters within the course. Within the course, yes, because I do not. I do remember that in the near future, the our faculty will in purchase for 3D printers, but the polymeric material printer. But I do not know when they will purchase the 3D printers. It's just a proposal, but I do not know more than that. Hopefully that you have time before graduate to practice somehow with the printer at school or at the academy. Hopefully, just an information. Inspire design. The design process can start with the requirement. So this is normal design process, I would say, because we start with the requirements, uh, containing, for example, the function of the part, the size of the part, the material that used to make the part, the weight, strength, dimensional accuracy, or even the cost. And based on the requirement, the designer can design the part to find out which type of geometry of the part will be appropriate. Sorry. In aerospace field, automotive or medical field, uh, there is a focus on the part qualities. Yes, on the certified material, the process and design, rather than on the cost or the aesthetic. Yes, because the most important thing is to guarantee the performance of the machines. And if the part is expensive, I'm sorry, I have a cold. I need to answer right now. Sorry, for a minute. Okay. here. So for this type of machines, we need to pay more attention to the safety working condition. And if it's expensive, and then it's still okay. And we pay more attention to the part quality rather than the cost and the aesthetics, how it appears. We do not pay so much attention to the aesthetics aspect of the part. And there are two actually approaches regarding the design process, called the top-down design and the bottom-up design. The top-down design is somehow the engineering design, because we start from the design function, meaning of design and how it behaves. So focus on the effective use, yes, or the safety use and so on. The bottom-up design start with the feeling about the design. So it's like an artist, yes, yeah, thinking about the feeling for the design first, and how it appears, how it attracts the designers. So based on the emotion of the designer, yeah. And it's not the engineering approach actually. The engineering approach is based on the requirements, based on the function or functionality of the part. And if the part is functioning well, it's okay. And a balance often needs between the design complexity and fabrication abilities. Yes, of course. And that's the reason that we need the additive manufacturing process in order to fabricate the complex part. Yeah. Because not all parts can be fabricated by traditional manufacturing process, despite the fact that these processes have been developed for, let's say, 100 years, more than 100 years. Because the first industrial revolution started, I do not remember exactly, but it's around 18,000, whatever. Yeah. So more than 100 years, more than 100 years for the development for the traditional manufacturing process. And now recently we have had the development of additive manufacturing. So and the fabrication by additive manufacturing is quite suitable for the complex design. Yeah, quite suitable. And the design tool for the additive manufacturing can reduce the complexity of use and help the designer to focus on their design rather than the manufacturing process, because there's almost no manufacturing restriction for the additive manufacturing or geometric restriction regarding the part if the part is fabricated by additive manufacturing. So if you could see on the right side, and traditional manufacturing process, yeah, can cannot be used in order to fabricate this part. Even you use the casting process, but it's been quite difficult to fabricate this type of part because it has the complex internal flow channel inside. So the drilling process, drilling one, cannot be used. The casting maybe you, but then the most uh, compatible, let's say, manufacturing process to fabricate the parts, yeah, I would say additive manufacturing, because with the approach of layer by layer manufacturing process, we can fabricate the part, but then we need to pay attention to uh, the anisotropy of the synthesized part or the fabricated part. It need to be carefully checked after the part is built. Okay. The workflow of the design process. So we start from uh, actually this is the additive manufacturing process, not the design only. We have the initial concept. Yeah, the initial concept is quite important, and sometimes we need to draw it manually, to define the concept first, and then we uh, start with the design, material selection, process parameter selection, and the fabrication of the prototype. And on the previous slides, we have talked about the bottom-up approach, and this was based on emotion. And you know that with this we need the inspiration of the material, yeah, and the material can rise or can help them to think about the idea of design. Yeah, inspiration of the material, shape, form, color, texture. Yeah. So, for example, in the field of Jura design, yeah. So, engineering design relies on more on the top-down approach. Yeah. And we need to find balance, yeah, with the resource and the constraint. And below you have the some kind of flow chart. So use the how can the design for additive manufacturing help you in save weight, integrate function, add the integral feature for sure, engineer surface, tailor material, and improve agility. And in saving weight, you can combine the design with structural optimization. We are adding the lattice structures instead of using the solid material, running the topology optimization in order to eliminate unnecessary material, using the generative design tool. So as I already mentioned, you have the generative design tool in Autodesk Fusion 360, and they have the artificial intelligence inside and help you to issue multiple results for one run of topology optimizations. And you have multiple results actually. And these results are the optimized structures, and therefore uh, those material, unessential material have already been eliminated, and therefore you have the lighter structures. Via the material substitution, yes. Initially, you have the part made of tin, and now you substitute the material by, by aluminum alloy. So for sure, is because the density of aluminum just around one third that of steel, and therefore is reduce the weight of the part. But it's not actually the design for additive manufacturing. Integrate function, because when you use the additive manufacturing, you can actually combine the structure of several components together uh, to enhance performance. So previously, with the traditional manufacturing process, for example, you have to divide one component into 5 different parts. So let's say, but with additive manufacturing, you can redesign the component and combine 5 parts together. Just an example. Just an example. I will not show you a figure on this slide regarding integrate function, but simply thinking of the fact that you can join different parts together, optimize the structures, print out with the additive manufacturing, and therefore it helps you to reduce the example step. Yeah, reduce the example step and save the cost for example line and integrate function. Because each part has its own function. When you combine different parts, you can integrate function into one part, yeah, one complex part. Uh, Add internal features like, for example, conformal cooling, separate foot flow, improve heat transfer by create different kind of brief wings, yeah, to transfer, to increase the area for transferring the heat to the surrounding environment. So yeah, you can add features for sure. Uh, Engineer surface to enhance the surface effect. Yeah, it could be. It could be in the case of medical field, for example. So when we talk about the hip joint replacement, there there is a component called the acetibular cup. Acetibular cup. Yeah. Nó là cái các bạn tưởng tượng cái acetibular cup thì nó giống như một cái cốc đúng không? Nó là cái xương đùi xương đùi của người ấy, thì có một cái kết cấu nó giống như là cái đầu xương nó tròn tròn ra đúng không ạ, và nó sẽ đưa vào cái cắp và nó sẽ di chuyển xung quanh cái cắp đó. Thế thì ở những cái người cao tuổi ấy, thì cái cắp đấy nó bị mòn mất rồi. Ở người cao tuổi thì cắp đấy bị mòn mất rồi, thì cái acetabular cup cũng như là cái hip joint này nó phải thay, người ta phải thay đi. Bác sĩ phẫu thuật thì người ta sẽ thay cái khớp háng của bệnh nhân đi, thường là của người già người ta hay bị. Thế thì acetabular cup này thì người ta có thể dùng cái phương pháp in 3D để tạo ra một cái bề mặt rất là nhám,